Okay, so take your test 11 by Monday. There's some lab committees if you want to sign up. Your lecture from last time was here. We're going to do lecture today. We'll finish up the chapter on, so this is off on days, you can tell. We'll finish off the chapter on Monday. And then what we're going to be doing is we'll do on Wednesday. Do I have AP test children on Wednesday here in this class? Wednesday morning? Okay, so how about Friday?
Wait, for what?
For AP testing. Are you going to be out next Friday? Anybody? Okay, so next Friday we'll do the polymer lab. And then after the polymer lab, we'll have you hand in your lab notebooks. I'll get those graded and in. Okay, and then, like I said, you have until the 24th to finish the test on chapter 12. And we're done. Oh my gosh. Okay, so let's go ahead and get going with today with the lecture. And let's see where we can go from here. Oh, I did have the light on. How many remember from last time Markanoff's rule? What is Markanoff's rule? Rich get richer and poor get poorer with what? Hydrogen. Hydrogen is the wanted quantity or wanted commodity. So as we're looking at this cyclopentene, methyl cyclopentene, by the way, what I'm going to do is I'm going to look at both sides of the double bond. I'm looking at those carbons. So as I look at this carbon right here, how many hydrogens does that carbon right there have? It doesn't have any because it has a double bond this side. It has a single bond, That's already 4. So it has 0 on this side. So that's my 0. What about on this side? How many does this one have? This one has 1. So this hydrogen is going to come on to this carbon, and this chlorine is going to come on to that carbon. Okay, that's Markanoff's rule. So as I redraw it, the double bond goes away. So I redraw it with my pentagon, and I'm going to have a CH3 and a chlorine attached there, and I'm done.
So they always attach to the double bonds?
Yep. When they attach to the double bond goes away. Okay? Ready to do another one? I'm just going to draw it because we've got enough room right here. Let's go through and do, I like cyclohexene. And let's put a chlorine on this side. And this time we're going to add hydrogen fluoride. Okay, predict the product. I want you to try it on your own. Predict the product. Now, they'll often won't write it like we've been writing it here. They'll just write HCl and they'll just write HF. Okay? But you need to know that they're separated by a bond, right? How do we do? Thumbs up, I got it. Thumbs down, I didn't. Oh. It's like, yes, this is what? Thumbs sideways, okay.
Oh, no, I think I did it.
Okay? All right, do we have any questions? The hydrogen actually went right here, and the fluorine went right here. But we don't show the hydrogens, right? The hydrogens are there. They make up to 4 bonds. But on a skeletal drawing, we don't draw the hydrogens. Okay, now these are all addition reactions, meaning I'm adding something to breaking the double bond or breaking a triple bond. Okay? So in halogenation, I'm just adding a halogen. So the halogen, one of them goes on this carbon and the other one goes on that carbon, and that's how I get this. Now, I wouldn't necessarily draw it just like this. If I'm doing a skeletal, it would just be like this. It would show them coming in on both sides. But we know with our conformations that it can twist, right? So we can twist. So if I have chlorine, which is a big molecule, and I have hydrogens, which are a small molecule, what's the chances that it's going to be eclipsed, with this being a big molecule and this being a big molecule? Probably not so much. They're going to be wanting to be away from each other. So they'll be eclipsed like this or like this, but they don't like to be eclipsed this way. So even though I've drawn it that way, that doesn't mean I'm going to end up that way. Yes?
What's the other word then?
Eclipsed or scattered, or staggered, sorry. Scattered is what my brain is right now. Okay, so we get it eclipsed where we like this, or we're staggered like this. Okay? All right, so going on. So halogenation, I'm adding a halogen, fluorine, chlorine, bromine, iodide. Okay? Hydrogenation, I'm adding hydrogen. So if I add a hydrogen, I add one here and I add one here, and I just break the double bond up. Done. So hydrogenation just breaks up the double bond or triple bond. Yes?
So for hydrogens, like, do they also want to be eclipsed, but like just...
Hydrogens don't care. They can be eclipsed or they can be staggered. They just don't care. They're so small, it doesn't take up much space. Yes?
They break up triple and double bond?
Right. So I can take hydrogenation, for instance, and take a triple bond here. And if I add one hydrogen group, then it's going to, one hydrogen here, one hydrogen here, it's going to break down to a double bond. Then I can still add more hydrogen, and it would break down to the single bond. Okay, so be careful, because she might put right here a 2. So if she puts a 2, then you've gone straight to there. Does that make sense? Okay. Same thing up here with halogenation. You can add, if I've got double or triple bonds, I can add twice as much hydrogen, or twice as much chlorine, or twice as much bromine. Okay, so I can do that. So be careful there with that one. The next one, so hydrogenation, yes.
Why do they have a triple and a double bond? What one would you want to apply it to first?
You have, if I'm starting with a triple, I take one away and it becomes a double. So
What happens if you have one that, like a formulation that has a triple and a double?
she won't give you that. That's more advanced. But it would attack which one's more stressed? Triple bond. It would attack the triple bond first. Okay? But she'll just give you with one bond, either a double or triple. Okay? All right, so hydrogenation. So halogenation, hydrogenation, and now we got hydration. So halogenation and hydration, halogenation and hydrogenation, they're the same element. So it's 2 hydrogens or 2 chlorines or 2 bromines or 2, they're the same. So it just goes one on each side of the double bond or triple bond break. When it comes to hydration, we go back to Markov-Off's rule. Because water will break up H and OH. It doesn't break up H and O, it breaks up H and OH. So we have one that will go on one side and one that will go on the other. Since both of these had 2 hydrogens to start with, it doesn't matter which side, right? But if I do a hydrogenation in which I have something like this going on, and I add water to it, where is the alcohol, or the OH part, going to go? Now, she's not going to write water like this. She'll write it like this. So you got to remember, oh, that is H and OH, right? So then I look and I say, okay, how many hydrogens are on this one? 2. How many hydrogens on this one? 1. Okay, so the rich get richer. So the hydrogen's going to go to this one, and the hydroxide, or OH, is going to go to that one. So when I make my final thing here, I'm going to have C-C-OH-C. So I get what's known as a secondary alcohol, or isopropyl alcohol. Which is rubbing alcohol. Okay? Iso, remember, just means it's the same on both sides of the alcohol where it's attached.
So I thought iso-al that came off the chain, but the chain is... The chain is
It's iso. It's the same off each side. So we would also, the isopropyl alcohol is a common name. This would actually be named 2-propanol. But that's later, gone down the road. Okay? All right, so let's come back here. We've talked about monomers and polymers when we defined them at the beginning of this chapter. But let's break it down. What does mono mean? One. What does mer mean? Okay, so poly means many, and mer again means part or parts. Okay, so polymer means many parts, and monomer means one part. So when I have ethylene and I want to make something with ethylene, okay, I want to make a polymer. This is my starting material. Okay? When I put it together to break that double bond, I have to have another CH, double bond C, H, H here, coming and bumping into it. Okay? When I do, this bond goes to one, this bond goes to one, and they connect. And they have to do that, keep going and going and going. So it makes a long chain. How we write that is like this. So this is the part that's going to keep repeating, and I don't know how many times because the chain can be really, really long. It can keep building and building and building and building. But this is the base thing. This right here is the monomer without the N there. That's the monomer. If I put the N there, that becomes the polymer because it's a repeating. Now what she would do is she would give you something, and well, let's do the next one and then I'll show you what she'll do. So the next one, again, we're going to put these two together. So this becomes a single bond. This is going to attach, and that becomes a single bond, and it's going to attach to something else. So over here, we would write, and I'm not going to write the hydrogens, so we'd put a parenthesis. It's going to repeat. Sorry, my line went a little long there. It's going to have two C's. On the second C, we're going to have a chlorine. Then we're going to have another C. Then we're going to have another C with two chlorines on it. And that's going to repeat. It's going to keep repeating to who knows how long. So what she might give you on the test, instead of drawing it like this, she might say, here's two things and they're going to make a polymer. Show me what the polymer is going to be. That's what you would do here. But she can also give you something like this. And say, what's the monomer of this substance? So how would I know? Well, what's repeating? If I look at it, this right here, and my yellow is not working. Try orange. This right here is what is repeating, right? So that's what I would put, C, 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 Br. That's my monomer. Now, how do I know what's going to happen with that monomer? Well, I've got to go back and say, okay, what made that up? So in order to make that up, I've got to have a double bond. I've got to have two double bonds. I've got to figure out where that double bond goes. Okay? And I picked an ornery one, but this would go away and we'd have a double bond here, and then it would attach back and forth. So you have to have a double bond to shift, and this would go away. So that would be my original. Okay? All right, next page. This next page is a little messed up on yours, so you might want to write it off to the side of that page because the formatting sort of went wonky, and I didn't realize it till after I printed your study guides. So, anybody remember what this kind of stuff is called when we do this? When we do the arrows like this.
Electronic configuration.
Electronic configuration was 1s2, 2s2, 2p2, but this is before the electronic configuration. Everybody remember what it's called? Orbital notation, right. So I'm showing where every electron is, what spin they have, what orbit shape they're in. This is orbital notation. In an unhybridized carbon atom, we have the S shell, which is a sphere. We have we have the 2s shell, which is a little bigger sphere. And then we have the 2p orbits that go like this and one in and out of the plane. What happens when we hybridize is we still have that 1s orbit, but we combine this. Remember that this one, we can't open this room right here, this orbit, unless we do it from inside the atom itself. So this one wants to jump up there and have its own room. It doesn't want to share because they're both in level 2. So what happens is it jumps up, and when it jumps up, they all are up and they're all equal. And we end up with a big side and a little side. And so we end up with our tetrahedral, remember there's one going out there in the back, I'm going to shade it a little bit, tetrahedral shape. Okay. So this is where we get the carbon and silicon and being able to make diamonds and stronger substances. Because of this tetrahedral shape, that 109.5 degree angle is very, very good at holding on to stresses without breaking. Okay, I'm going to zoom out a little bit more again so I can get the whole page. Okay, so let's go down to talk about a triple bond. We've sort of already talked about it before. Remember, in a triple bond, we have 1 sigma and we have 2 pi's. 2 pi bonds. Remember, sigma is your s, pi is your p's. So as we're looking at it, we have a sigma bond and a pi bond. And when we get to this shape that we had up here, this is known as an sp3 hybridization. If I'm bonding, I can bond sp3. So we have this shape, this tetrahedral shape that we've made down here, and I'm going to do that shaded part back in the back. And we have another one that's also been hybridized with our little shaded person back in the back. And in order to do a triple bond now, because the S and P are all about the same, is now we have to bond this one to this one, this one to this one, and this one to this one. That leaves a one that's standing out back on its own. Okay? When we do that, it forces it, like we did up front when they had to hold their hands and put one knee to one knee, it forces them into a linear shape. Okay? Okay, so we get to name alkynes. I'll call them alkynes. They're actually alkynes. Okay, but you'll hear me call them alkynes all the time. So to name alkynes, we do the same kind of thing that we've done before. Here's a general formula. And what do we do? What do we do with alkenes? Number it shortest to the bond, right? So we'd number them 1, 2, 3, 4, 5. 5 is what? Pent. So, and there's a triple bond, so I can say pent wyne because that's the only thing that's there. Where's that wyne at? At 2. So I go 2-pent wyne. Now, if there were other things that were changing the ending, I still would do the pent, but I'd put that 2 right before the yne. If the one triple bond is all I have, this is the preferred. Okay? So let's do another one. I'm going to add a little bit of review of everything we've learned into this next one. So this is going to be hard, but not hard. Take it step by step. Okay? Here we go. Bond goes first, but you have to be alphabetical on this one.
So if there's 2 of something and it's died, does that change the alphabetical?
Nope, the prefixes don't change it. It wouldn't anyway on this one. Okay, I'll give you another 15, 30 seconds, something like that, to see if you can get it down. And I'll show you the answer. We'll see how many thumbs up we get, how many thumbs sideways.
Why would you go 4, 5? Because there's more bonds. That's just wait, no. But there's also 3 bonds. Wait a minute.
Okay, how do we do?
No.
How many forgot the trans? Okay, don't forget that. At a double bond, if they're opposite or if they're on the same side, you have to put cis or trans. Okay? Why did I number the way I did? Yeah.
It's because there's triple on both sides, but the next one.
It's not triple on both sides.
Because you have a branch off the first one, goes to the fin, but the other one doesn't think that comes off the first carbon.
So, but bonds, Jane Bond would always go first. So why would I name that the way I did? Because either way, starting here or here, it's going to be 1. Why did I choose this as 1?
Because there's a
What is a double bond? What do I change the ending to? E-N-E. What is a triple bond? Alphabetically, E-N-E comes first. If they're both on the same carbon, yes. So they're both starting on the same carbon. They both would have been 1. So E-N-E comes first. That's why I changed it down here. So when I do this, what I do, okay, is I always work with the main chain first. I ignore the rest of them. So here's my main chain, right? Here's my main chain. So once I've got the main chain, then I say, oh, okay, I've got a double bond here and a triple bond here. Then I decide which way I'm numbering. Once I figured that out, I know how many, and then I look at the alphabet, right? And then I put those in. Once I've got that done, then I can come back and say, okay, I have a methyl group, and I have 2 bromine groups, but they're at a double bond and they're opposite, so I've got to do the trans. Does that make sense? So I take it step by step by step. Yes?
So you only use cis or trans on like triple or double bond?
Only on double bonds or cyclics. Okay, double bonds or cyclics are the only ones that could do cis or trans because it's locked in to place. I'm locked into that up or down at a double bond. Okay, and I'm locked in when it's a circle. It can't flip because it's locked into that circle.
So double and circles?
Mm-hmm. And cyclics. Okay, yes?
So when we name the first part, we're naming like the stuff that comes off.
The stuff that's coming off,
And
yep.
the bottom part, we're specifying that it's a pentane, then with a 1, or the double bond after the 1, then the triple bond after the 4.
Right,
Okay, that makes sense.
right. Okay, any other questions? Are you getting this? This one was a sort of summary of everything we've learned so far. She won't give you one that hard. Okay? But I wanted to see if you remembered everything. She'll separate the cis and the trans. She'll separate that kind of stuff. Okay? Just a reminder, when you go take test 11, make sure that you sort of cover up the answers, write it down, then figure it out, then look at the answers. Okay? All right, let's look at the next thing here, 12.5. We have talked about benzene rings before, but this is where we're going to go into benzene rings a lot. These are the expanded structure of a benzene ring. It can go back and forth because it can spin in space, so we don't ever really know exactly which one's a double bond and which one's a single bond. But if I were to name that, normally it would be 1,3,5-cyclohextriene, or you could do cyclohex 1,3,5-triene. Well, we use benzene so much and it's in so many compounds, they got sick of doing that and they just named it benzene. So anytime I see this structure, it's a benzene. And we also got sick of trying to decide where exactly those lines would be because they spin in space. So we put the circle. Now, to sort of explain this circle, when that hexene ring binds, there's only one pi that's not bound, and that's pi z. Because of that, those electron clouds and that shifting double bond, these actually become a donut shape of electrons. So we have a donut on top and a donut on the bottom. That's where that circle comes from. Okay, so that's the explanation. It's what we call delocalized electrons. Okay, so when it says delocalized here, it's talking about the electrons. It's not talking about the bonds. Okay? All right, going on. Okay, this is the last page I'm going to do with you today, and then I'm going to leave you to your lab, and we'll talk about that lab in just a second, and or your sapling or whatever needs to be done. So, when we're looking at benzene rings, there's some things that we use with benzene so much that they've been given a name. This is one of them. This would have been called, if we named it as is and didn't know any special name for it, methylbenzene. But that's not the name we use. We instead use, oh, am I too high? So, thank you. So we instead use toluene. Don't ask me where they got that name. That's just the name they gave it. So anytime you see a benzene ring with a methyl group attached, because they are so common, remember these are things that we use a lot, that they've given these common names to, we use toluene. Now, there's also positions coming off of a benzene ring that have specific names. So instead of saying 1,2-dimethyl benzene or 2-methyl-toluene, what we do instead is, since these are right close together, it's known as the ortho I can spell, position. We just put an O, and we treat that O as a number. So this would be O-methyl-toluene. This one right here, you have one space in between that's not occupied. I remember that as meta, because I just met you, so give me some space. Don't get in my personal bubble. Okay? So orthodontics, teeth want to be right next to each other. Meta, one between. And then para is exactly opposite. So these were all methyltoluenes, but this one is O, this one is M-methyltoluene, and this one is P-methyltoluene. Okay, it only works with benzenes, and only when you have two things coming off. Okay, if you have three or more, it does not work. Okay, so let's look at this one over here. I'm going to draw you one, and I want you to name it. Okay, so anybody think they got it? Being brave. Anybody want to venture a guess? M is right.
So M1.
The ethyl,
Ethyl is right.
and then methyl.
Nope.
Dang.
What is this that I had to start with? What was it called? Yeah.
That
Toluene. Done.
makes sense. I am not sure. I overcomplicated it.
Yeah, don't overcomplicate it. A benzene ring with a methyl group is a toluene. Yes.
What if the one on the top was also methyl?
If the one on the top was an ethyl, then I would have gone M-diethyl toluene. Or not toluene, benzene.
We're not saying
Why don't we need the other one's dimethyl?
Because the methyl is included in the toluene.
Oh, yeah.
Okay? All right, so let's go over here. These have specific names. This one, what do you think?
Dimethyl.
Don't make it too hard.
Non
What is this and what is this?
benzene with ethyl.
So there we go, ethylbenzene. Do not make it too hard. Okay, this one gets a little bit, this one is part of explosive stuff, so what is this?
Is that a nitrate? Or
Almost.
nitrite?
Nope.
Nitrate.
Nitro. And then I put benzene. Now, she can write the benzene ring this way or this way. Just recognize it as a benzene ring. Okay, make sure it has 3 bonds though, because she'll throw one that has 2 and it names differently. Okay, what do you think this is? Bromobenzene, yep.
Wait, if it is double bond, and then
It's got to be every other one a double bond to be a benzene. Okay, what about this one?
Chlorobenzene.
Chlorobenzene, yep.
What are these kind of like things used in?
What?
What kind of like substances are used in?
These are used in medicines a lot.
Be like bonded with most things?
They'll be bonded with something else. Okay, so this is what? Toluene. Yay, you recognized it. Okay, these two are actually the same, and they have a special name. It's a benzene with an OH group, but we don't call it benzene. We actually call it phenol. Remember what phen-YL was a benzene ring attached to something? Well, an OH is an alcohol. So we changed the ending from phen-YL to phen-OL, saying it's attached to an alcohol. Okay? This one right here, what do you think? This one has no rhyme or reason.
What? I quit chemistry.
This one you got to just memorize.
No one of these substances like that.
Okay, but this is used a lot in biochemistry and organic chemistry. So that's why it's given its own name. Just like benzene. Did it have anything to do with cyclohexene? No. Okay. What about this one? Anybody recognize this group right here?
aldehyde.
Almost. Aldehyde would just be like this, but this has the OH also on the ending. So it's one of your groups that you just were learning about. Ketone would be a double bound oxygen in the center.
Acid.
A carboxylic acid. So normal inorganic acids we do ic and add acid, right? Well, in organic acids, we add an oic. Okay, so this becomes benzoic acid. And all organic acids are icky. They're icky. They're really slimy, nasty, awful things. Okay, so then we come down to this one right here. Now we have this long chain attached with a benzene ring. Well, we're not going to use the benzene ring as our main chain. We're going to use this as our main chain. Because I don't know how to name this attached on the 3rd carbon, right? So what we do is we say, okay, we're going to number this slowest number to get there, right? So it's at 3. And when a benzene ring's attached, we just went over that just a minute ago. It starts with a P. Anybody remember what the name was? Phenol. And 7 is heptane.
So when it's just attached to phenol, but it was attached to alcohol.
Phen-YL. Yeah. So you got to know the difference. A phene YL is something attached to a chain. A phene OL has an alcohol. Okay, now this one I call the butterfly down here. And you guys are actually going to make something like that in your lab that you're doing. By the way, it'll probably take 2 kits, so you might want to be working with your partner when you get to that one. We're still going to number the main chain going through the center. So 1, 2, 3, it didn't matter really which way I chose, so I just chose forward. I have 2 phenyl groups coming off. How would I name this? It would be a diphenyl. What would I put in front of the diphenyl? And remember, you have to put 2 of them. If there's 2 things there, I have to put both numbers. And what was the ending on this one? Pentane, good. Okay, so here's a review real quickly about what was on the top. This, when it has 2 methyl groups, we can call it xylene. Okay, so this would be O-xylene, M-xylene, and P-xylene down here at the very bottom. Okay, that's just methyl groups. Those are just methyl groups. So if 2 methyl groups are coming off a benzene ring, then I get a xylene. And the position, the ortho, the meta, or the para, O-xylene, M-xylene, or P-xylene, just tells me what position those methyl groups are in.
So if it's not methyl, then it's...
If it's not methyl, then I have to say what it is. This one tells me I have 2 methyl groups attached. The O just tells me the position they're in. Okay, xylene just tells me there are 2 methyl groups attached to that main chain.
So then with this, we no longer call like the O-xylene the O-methyl carbon.
Right. Okay, so this is just another specialty thing. Okay, we can use this. Okay, with other things, but when it's 2 methyl groups, I just use this right here to show you how it would work. But the real naming of it is down here. Okay? All right, so let's talk a minute about your lab. On your lab that I just gave you, look at it real quickly. This is all about drawing and making models that have to do with double and triple bonds. Okay, and halocarbons. So we're going to be doing a lot of bending and making molecules. I would suggest that you work with your lab partner because you're going to need 2 kits for a lot of them. And it's a lot of pulling and pushing, and I don't know about you, but my fingers get really, really sore after pulling these apart so many times. Here's the key. Look at the instructions. What do the instructions say on this one? It's different. Kylan? Some of them are named wrong. Guess what? On your first one, there was one that was named wrong, and I want to make sure before you turn it in, you change that to the right name. So there's one on the first lab that was named wrong. She loves to do this. You can still build the molecule, okay, with it named wrong, but then I want you to name it correctly. So you get used to seeing mistakes. Does that make sense? Because when she actually writes that in on the test, if you're naming it wrong, it will show up. Okay, but I want you to realize it's named wrong that way. Does that make sense? Okay, so time is for you to work on your sapling, to work on this lab, to work on your quizzes, whatever needs to be done. Thank you. Oh. Okay, I was like, Okay. Time is yours. Yes?
So skeletal's the one with like the
Skeletal is just with the carbons, not the line, but the carbons, no hydrogens.
and then structure drawing.
Structural, you're showing me this.
So we would include like a line.
The colors and everything the same, yes.
So the lines are also showed between the bonds.
Yes. Okay, anything else? Okay, time's yours.